All right, welcome back to week 8 of our graduate statistics course. We're beginning to do inference, statistical inference using t-tests. And here we're in a situation where we want to know whether the question that we're trying to answer is whether distraction during one meal modifies the amount of food consumed later for snacks. And we have the amount of food that distracted eaters ate. And to answer question 2, we need a basis for comparison, and we're using as the basis the serving size. We're assuming the serving size is the average that individuals in the population eat. I get it, that's a push, but that's what we're assuming here to move forward and try to get our first pass at answering this question. And we finished last time saying that we already have a quick and dirty way of answering this question, and saying that no, it's different. When you're distracted, you eat more than the serving size because 30 is not contained inside that interval. So this is the quick and dirty way of assessing the non-directional hypothesis that we have here. We're using the 95% confidence interval. Again, the null hypothesis here to formalize is that the average snacking amount of distracted eaters is just equal to 30, the serving size, that we assume is what the general population eat. And the alternative is that it's different from 30. So it's a two-sided test and an alpha level of 0.05. Because it's a two-sided test, it has to be distributed in the two tails. So 2.5 on one side, 2.5 on the other, leaving 95 in the middle. So a two-sided test goes together with a 95% confidence interval if you want to use it to do a quick and dirty hypothesis test. Okay? All right, so here it is. Illustrating the two tails. I have to, on a two-sided, I get my 5% rejection probability, and divide in the two on the two sides. So 95% in the middle. That's why two-sided tests goes with 95%. If I'm running a one-tail test, I basically ignore one of the sides. If I'm doing a less than type of directional, I put all 5% on one side, right? And then the boundary here will be together with a 90% confidence interval for one-sided tests. All right, so the confidence interval here would be 32.1 to 72.1, right? And our observed value is 30, so 30 falls in the rejection area here. So we reject the null hypothesis that way. All right, that's why these two intervals go together. This is a high, the two-sided test goes with a 95% confidence interval, because if you have the boundaries here, you can assess whether the value that you are using for the null hypothesis falls in the rejection area or not. And it will fall in the rejection area if it's outside the confidence interval on either side. All right. Now, suppose the suggested, so we're continuing on, sorry. We're saying, suppose the suggested serving size is 30. Do these data provide convincing evidence that the amount of snacks consumed by distracted eaters post-lunch is different from the suggested serving size? We did that quick and dirty way, but when we do it that way, we can't compute the probability of observing our average snacking amount under the null hypothesis, right? So you need a test. Because we have one random sample only, we just have one sample of distracted eaters, and we're comparing that to a benchmark value, average value, then we have what we call a one sample t-test that we need to apply. So we have one sample of distracted eaters where we have the X observed of 52.1, and we have our null hypothesis value, that's 30. And then one sample t, we get the X bar, which is the mean observed, and we want to subtract the mean related to the null hypothesis to see how distant from the null hypothesis the observed is, and divide by the standard error because we want to know the distance in standard error units, standardized units. So here is the computation. So we have a t-value of 2.3 on a t-distribution of 21 degrees of freedom. And here we have, it's a two-sided hypothesis, we have 2.3. So we want to know the probability of getting 2.3 or more extreme, absolute 2.3 or more extreme, which means the probability of getting 2.3 or more, plus the probability of getting negative 2.3 and less. What's that probability? So I can use this piece of code here, 2 times the probability of getting the absolute t-value or more extreme for what do we call a t-distribution of 21 degrees of freedom. And we're saying that we want the upper tail because we're using the absolute t-value, which is going to be a positive value. So we want this one, and then we multiply by 2 to get the probability. Oops, what's the probability? Oh, shoot, hang on. Apologize about that. I'm back with the p-value. So if you run this in R and you put the value of 2.3 here, we get a p-value of 0.03, which is less than 0.05, suggesting that the rejection area, 2.3 would fall in the rejection area. And the probability is pretty low of observing that t-value, which suggests that the null hypothesis should be rejected in favor of the alternative. All right? So now let's move on. So what we just did was to compare we just had one random sample, and we observed their average, and we wanted to see if it was different from a benchmark average, right? Kind of like we did for the z-test. Now, what if I want to make an inference that relates 2 different groups, 2 different averages coming from 2 different samples? How is that done, right? So then we really don't have much of an option than to run a t-test. Let's see how that plays out. Same question. We're after understanding the role of the impact of distraction on snacking. That's what we're focusing on. Now imagine you have a sample of 44 participants, not patients, participants, 22 men and 22 women. And here is the study design. These 44 participants were randomized in 2 groups. One group is the one you guys engaged with just now that played solitaire while eating, and they were told that they need to win as many games as possible during lunch. The other group ate lunch without any distractions. Both groups were provided and ate the same amount of lunch. And then later on, they were offered biscuits to snack after lunch. Now here's our summary statistics. The group that played solitaire ate 52.1 grams of biscuits that they were offered after, and the no distraction group ate 27.1. Just by looking at the average, we see a difference there, correct? That the group of people that ate while distracted, ate lunch while distracted, ate more than the other one. Now again, it's consistent with the hypothesis that distraction leads to more snacking later on. Distraction during lunch needs to lead to more snacking later on. But it's not sufficient, is it? Because if I were to get another sample and put half distracted, half not distracted, and compute the averages, it is not going to be exactly 52 and 27, is it? It's never going to, even if distraction did nothing, we would not expect the 2 groups to eat exactly the same amount and the difference be 0. The difference will always be some fluctuation, will always fluctuate. Even if in the population at large, distraction does nothing, we would not expect the mean to be zero, the mean difference to be zero every time. We would expect that mean difference to fluctuate. How much does it fluctuate? Would it be normal under random conditions where distraction did nothing? Would it be common to see a difference as large as this is the question. What is the probability of observing a difference as large as this one that we're seeing? Okay. With that in mind, let's go back to our questions. We want to know what is the difference in the amount of food consumed at snack time between individuals that were distracted and those that were not. We can compute, of course, the average difference here, but it would be nice to have a confidence interval around it, just the same, so we have more confidence. We're not fishing in murky water with a stick. We're fishing for the true difference with a net instead. So we want a confidence interval around the mean difference. And question number 2, does distraction during one meal modify the amount of food consumed later for a snack? This is a good design to assess that, right? Because we have 2 groups that were randomized. They were similar in many, many ways because they were simply randomized in those 2 groups. They ate the same amount of lunch, and then we were observing the difference in snacking afterwards. So it would be nice to see if there is a reliable difference between these 2 groups, if the difference is large enough to be unlikely if distraction made no difference, right? Then we can reject the null hypothesis in favor of the hypothesis that, yeah, distraction does something, right? So let's see. What are the conditions for us? Sorry, I'll put this down here for a second so you can read stuff here. So we're same title there and reading here. All right. So what are the conditions for me to run an inference for comparing 2 independent means with t-test? Independence of observations continue to be important. So within each group, the participants need to be independent from each other. I cannot have a bunch of snackers on one group and a bunch of people that don't like snacks very much on the other group, right? The probability of the amount of snacking of one person should be independent of the probability of the amount of snacking of the other person within the groups. We need to have random and sample or random sampling. I need to randomly sample for the population, or minimally in this case, random assignment. I should be randomly assigning participants to the distraction and non-distraction groups such that, you know, preference for the biscuit and the amount of usual snacking of the 2 groups is similar because they're being randomly assigned. And then the only difference between them is the presence of the distraction. If I were sampling without replacement, which is always true in studies, because we sample a person, we don't put the person back to run the risk of running that person again in the experiment, we need the sample size to be less than 10% of the population. All of these things should be true in order to guarantee the independence within the groups, within the observations, between the participants in the same group. Now, the 2 groups also must be independent from each other, and if they're not, there are things that we do. But when we have 2 groups that are independent from each other, then we run independent t-tests, okay? And then sample size and skew. The more skew in the population distributions, the higher the sample size needs to be in order for us to be able to meet the conditions for reliably running a t-test. In addition to all of that, the 2 groups, that's the important piece, need to have equal variance. The variability within each group in the measure that we're taking, in this case, amount of snacking, should be about the same. If this is violated, you can still run the t-test, but you need an adjustment. And we'll see that in the lab, how that's done. Okay? All right, let me pull this up, and we'll come back with the results of this particular test after a little break. See you then.